Visible?
Yes.
Okay.
You could make it full screen and then you'd be able to display everything all at once.
The problem is I've had problems with full screen. So as long as this is visible, let's leave it.
It's very visible, so there's no problem with on this side. Okay, so we're resuming with the Rothschild distinguished lecturer. He's going to present a talk on commuting sets in groups and algebras. So off you go, Bob.
Thank you, Chris. First, let me apologize for not being there in person. I would have very much liked to have been there to see all my friends and everybody who's there. There were various circumstances where I couldn't, and it's unfortunate that both Michael and I couldn't be there in person. But let me first thank the organizers. So Tiep and Britta, and the organizers of the workshop, Rada, Martin, and Chris, for all their work and for doing this. I should say that I got a proposal about probably 4 or 5 years ago now from the Newton to evaluate having a program in group theory. And I read it, it was a great proposal. And then at the very end, the last paragraph said, oh, and the last week's workshop will be for Bob and Michael. And I was thinking, at that point, I almost decided I should tell them no, they shouldn't do it. But I said, I figured, okay. I think Michael actually also got it to evaluate, but anyway. So I'm pretty much overwhelmed that this would happen, and also that I'm the Rothschild fellow. I mean, when I started doing mathematics, I started in graduate school 50 years ago. I certainly never imagined anything like this. So thank you to everybody, and thank you to people for coming. It's a little bittersweet because Kai and Jan are not around. I think I'm not sure I've ever been in Cambridge when Jan hasn't been there. So it's, of course, I'm not in Cambridge, so right at the moment. But in any case, it's this. It does. I miss both of them quite a lot, and I talked a little bit. We had the memorial for Jan on Friday. Kai's name will come up in the work, in part of the talk as well. Let me also say that this is, the conference was for Michael and me, and pretty clearly I'm the junior partner in this. Michael's contributions to group theory have been overwhelming and just immense. And so it's just to be even considered having my name attached to this with him is a great honor for me. But Michael has been, over the years, I mean, even when I was a graduate student, I had already heard about all the great stuff Michael had done. And then I was a graduate, then my first job was a postdoc at Caltech with Michael. And Michael has, over the years, he's been an inspiration. He's been a co-author. He's been a wonderful friend. He's been a mentor, an inspiration. And he's also written more letters for me than probably anybody else in terms of visiting positions and so forth. So it's really, I really like to pay homage to him. His contributions, which people have talked about so far, are just have been tremendous. And as Alex mentioned in his talk, John Thompson, of course, really revolutionized the field. But Michael has made a huge difference. And in fact, I think Danny Gorenstein once sort of thought it would take 35 or 40 years to finish. In some sense, he was right, actually. But he said then Michael came along and started proving amazing theorems. So one nice thing about this group theory community is that it's really like a second family. And so it's nice to at least have seen you. By the way, I should say I've been to all the talks, which, if anybody knows me, is rather amazing because I usually fall asleep by 9 o'clock. So, but so anyway, besides thanking Michael, there are a few other people who very early in my career were really very supportive, and in some sense, not for any particular reason, but they were. So let me just mention them very quickly, and then I'll start doing some mathematics. So Bob Steinberg, when I was at Caltech, Michael and Olga Towski and David Wales. And then in my first few years out, Walter Feit, John Thompson, Danny Gorenstein, Richard Lyons were all really amazingly helpful and supportive. So I want to thank them. All right, so I'm going to talk about commuting sets in groups and some related kinds of objects, and see what some of the directions that it leads to in various different ways. And since this is the Rothschild lecture, I was told that this is supposedly for a more general audience, although I'm not sure there are any non-group theorists really in the audience. I mean, Percy doesn't consider himself a group theorist, but he really is. So anyway, so let's start. So let's make the following very deep observation. A group is abelian if and only if every 2 generated subgroup is. Okay, that's not too hard to see. And so this leads to some interesting questions in lots of different directions, and I'll mention some of them as I go along. So the question is, what other properties can be determined just by looking at 2 generated subgroups? If you just know something about pairs of elements. Okay, so mostly I'm going to stick to finite groups, but not always. Finite groups, sometimes algebraic groups. But so what other properties can you say? Well, nilpotent groups, finite nilpotent groups, not all groups, but for finite groups is nilpotent if and only if every 2 generated subgroup is nilpotent. There's a much stronger theorem, the Baire-Suzuki theorem, but in fact, you don't need the Baire-Suzuki theorem to prove that. Okay, what else? Well, a finite group is solvable if and only if it's every 2 generated subgroup is. Now, the first proof of this was by John Thompson as a corollary of his N-group paper. So he classified in particular all minimal non-abelian finite simple groups. And you observe that they're all 2 generated. And from that, it's quite easy to see if you have a non-solvable group, you can find 2 elements that will generate a non-solvable subgroup. It was later proved by Flavel without using Thompson's work in a very nice paper as well. But okay. Well, we can generalize this because we now know more about simple groups as an application of the classification. Let's consider a family of finite groups that's closed under subgroups, quotients, and extensions. And we say G is an X group if it's in the family. And we know that every finite simple group can be generated by 2 elements. This was mostly done by Steinberg. He did it for the finite groups of Lie type after some earlier work by various people. So the same proof that went for Thompson shows that a finite group is an X group if and only if every 2 generated subgroup is. By the same proof, you basically can reduce to a case of simple groups. Here's a slight variation on this. Let's talk about the X radical of a finite group. So that's the largest normal X subgroup. So if we're talking about solvable groups, that would be the solvable radical of the group, but just the largest normal subgroup in which is an X group. And it's dependent on the classification. Is that if you have you don't need the full classification for this, but something's in the solvable radical if and only if it's generated, it together with any other element is a solvable group. And you can extend this to X groups. So an element X is in the X radical of the group if and only if it together with any other element is generates an X group. Let me just assume X contains all solvable groups, just otherwise the statement's slightly weird, but anyway. And the easiest way to prove it, you don't need this full result, but is a result of Tim Burness and myself and Scott Harper, a recent result that characterizes what are so-called 3/2 generated groups. That is, given any non-trivial element, there's some other element which generates the whole thing. You don't need the full force of that, but it certainly comes out of that. From that is that this result I stated. So that the x-rad, you can determine the x-radical in terms of this generation by with some other element. All right, so this is one direction where you can sort of extend. Now another theme that comes up and in much more general context, but you can say, okay, well, do I really need every pair of elements to commute to know that before I know the group's abelian? What do I really need to know that the group's abelian? If most of the elements commute, will that imply the group's abelian? And at least, well, you need some way of measuring that. So for finite groups, we have the uniform measure, or if you have a compact group, you can talk about it with a Haar measure. And then there is a theorem that says this. This is true. You don't really need to know all pairs. If you know enough pairs commute, then the group's abelian. And this has been extended in many ways, but in some very nice ways by Michael Larson and Anair, and Tiap has been involved with some of this, is that if you say work with profinite groups, not profinite finite groups, that's my first typo, not my last, I'm sure. If you have some law that holds with positive probability, then it usually means, or often means, that it's because the law holds on some coset, a finite index. So for example, in a dihedral group, you can look at the law x squared equals 1. Half the elements have that property, more than half the elements, typically. And that's because it holds on a coset. Okay. So anyway, here's a very old theorem of Gustafson that could have been proved, if anybody thought about it. If the probability, so for a finite group, if you just look at the probability that random pairs commute, if it's greater than 5/8, then G is actually abelian. And 5/8 is best possible because, for example, if you take any non-abelian group of order 8, the probability that the random pair of elements is commute is 5/8. More generally, if the center has index 4, which is the smallest non-trivial index it could have, then you get 5/8, and just from a trivial argument, you get this estimate. And if you impose some extra properties on the groups, you get better and better estimates. For example, if the probability of commuting is bigger than 1/12, then G is solvable. And that's, again, best possible. I think Dixon was the one who observed this. A5 is, of course, the counterexample you would think of is to compute the commuting probability in that. Okay. Now this came up in Gunther's talk. It's quite easy to compute that the probability that two random elements in a finite group commute is exactly K of G over the order of G, where K of G is the number of constancy classes. And so this problem really, in some sense, is just getting estimates for the number of constancy classes of the group compared to the order of the group. And there are all sorts of results about this, And so, if of course, if G is abelian, then this ratio is 1, but otherwise it's at most 5/8, and you can say more about what possibilities are for this ratio. So let me just mention in this context a result that Jeff Robinson and I proved. If you take a finite group with the fitting subgroup f of G, the largest maximal normal nilpotent group, then you can get an estimate for the commuting probability, or for the number of constancy classes. It's less than or equal to the number of constancy classes in the fitting subgroup times the order of G to the 1/2 power. So in particular, less than or equal to what I've written on the right. In particular, if the fitting subgroup is trivial, then K of D is less than or equal to the square root of the order of the group. And in particular, you can see therefore that if the fitting subgroup is trivial, then the computing probability goes to 0 very quickly as the order of the group goes to infinity, or more generally as G mod F goes, the order of G mod F goes to infinity. This depended on the classification, because you really needed to get estimates for this for simple groups, for the finite simple groups. What can you say about the number of constant classes? You can do a little bit better than square root. I think, depending on sort of the worst case, at least asymptotically, is for the two-dimensional PSL2s, where you're essentially getting the order of G to the 1/3 as the number of constant classes. Okay. A couple of other directions. I'm going to come back to this probabilistic aspect in a minute, but there's just a couple of other directions one could take if you were wanted to look at commuting pairs. You could what people do, and to some extent do too much, I think, is associate a graph to almost any kind of property that you can look for a finite group. Some of them are quite interesting. Some of them aren't quite so natural, but anyway. So there's the commuting graph. So let's assume the center is trivial, just to make life easy. You take the vertices of your graph to be all non-trivial elements in the group, and you connect them if they commute. So that's called a commuting graph, and people have done lots of work on this. Peter Cameron, in particular, has done some very nice work on this. I think he even talked about it, perhaps, during this program. And one of the really nice results of using this was a result of Yoav, Segav, and Gary Seitz. They proved some results about commuting graphs of the simple groups, and this had this very nice consequence about finite quotients of certain arithmetic groups. There was joint work with Yoav and Gary and Andrei Rapinchuk. I'll just mention another result that came up very recently that it was a question of Jeff's. He asked me is, it turns out, so you could just say, if you have two constant classes, are there elements in the constant classes which commute? And it's pretty easy to see that that's not, that doesn't always have to be the case. It's easy to find pairs of constant classes which no two elements commute. No pair of elements commutes. But Jeff asked what happens for involutions. So given a class of involution, two classes of involutions, can you find conjugates which commute? And more generally, can you find some abelian subgroup which actually contains conjugates of every involution? And it turns out the answer is yes. Again, this requires the classification. And you can even prove it for quasi-simple groups. It turns out that there's always an abelian subgroup which intersects every class of involutions. You cannot extend this for odd primes. If you get bored, you can try to write this down. Write down an example. And it fails for almost simple groups. You can't extend it, although it's very close to being true for almost simple groups. But the canonical example is an orthogonal group in characteristic 2, because there's an outer involution which interchanges two constant classes inside the simple group, which means it can't commute with anything in either of those classes, because it doesn't even preserve the class, let alone an element in the class. Okay, so let's go back to probability for a minute, for a while. With John Wilson, we proved a similar result to the 5/8 result for solvable groups. What's the probability that if you know that there's a large probability that a random pair generates a solvable group, is the group solvable? And the answer is yes. I don't remember exactly what the answer was, but I think it's basically A5 is the, whatever it is for A5 is the estimate. This depends on the classification. And you can, similarly for nilpotent groups, this was done by Jason Fullman and various co-authors a long time ago, I think in a undergraduate research program, summer program, although they assumed the group was solvable to get the estimate because, otherwise you really need the classification because you need to know the group's solvable in order to then try to decide whether it's nilpotent. And so once we prove the solvable result, the nilpotent result follows in complete generality. Okay, and you can do this for X groups. You can do this for sort of any sort of reasonable property. And the answer should be in general is that as long as you're that almost always you're bounded away from if the property fails, then it's going to be bounded. The probability that it fails is going to be bounded away from one. This is not always true, but mostly true. Okay. So as I said, this is really about counting conjugacy classes. And so one wants to get very good estimates for how many conjugacy classes are there, especially for, say, simple groups, or quasi-simple groups, or almost simple groups. And so it was mentioned, I think Percy mentioned this, but anyway, or certainly mentioned in an earlier talk, the number of conjugacy, maybe it was Gunter, number of conjugacy classes, say in the symmetric group, is just the number of partitions of n. And there's a similar estimate, very close to that for the alternating group. And there's very good asymptotics on that. For groups of Lie type, we sort of know the answer. Most elements are semi-simple elements, whatever most means. And then it just, as Gunter mentioned, at least if you look at the simply connected simple groups, Steinberg showed, and Gunter wrote down a formula for them in terms of maximal tori in the Weil group, is that the number of conjugacy classes of semi-simple elements is exactly Q to the R for a finite group of Lie type over FQ in rank R. And that's even for twisted groups interpreted suitably for the regroups. This is correct. So that's a lower bound for the number of conjugacy classes of a finite simple group of Lie type. And as I said, most of them are like that. So you want an upper bound. So the point is it's big O of Q bar. Now, but of course, what are the constants in that? And so Wall, at least for the classical groups, basically gave generating functions for number of conjugacy classes. And this is how I got started with Jason. I saw Wall's formulas and I said, okay, I just want an estimate. I don't see how to get an estimate. He gives you an exact formula. I want an upper bound. And I couldn't see how to do this, but fortunately Jason could. And so the upper bound is of the form Q to the R plus some constant, explicit constant times Q to the R minus 1 is an upper bound. And this explicit constant, I mean, it really is explicit and it's fairly small. I think it's maybe with no exceptions, you can take it to be 50 something. And most of the time it's much smaller than that. And moreover, this constant, as I said, it's explicit, and in particular, it doesn't depend on the rank. And as Q goes to infinity, even without respect to the rank, the C gets down to being very small. It's usually 1, 2, or 3 in the limit as Q goes to infinity, irrespective of R. It depends sort of what family of simple groups you're looking at. So we have very good estimates for the number of conjugacy classes, for at least for the finite simple groups of Lie type. Of course, for the alternating groups, we have these combinatorists, very good estimates there. And for the sporadic groups, we know exactly how many there are, and there's not very many. The monster only has 170 some odd classes, yeah, even though it has order roughly 10 to the 55th. So the commuting probability of the monster is pretty small. Okay. Well, applying this to SLNQ, I should say, not really GLNQ, but it really doesn't make much difference. For GLNQ, the number of kindness classes is pretty close to Q to the n. It's very close to Q to the n. And so you can see that the probability that two random elements of GLNQ commute is roughly 1 over Q to the n squared minus n. Okay. So as Q or n get big, this is going to 0 very quickly. All right, so instead of looking at n by n matrices, n by n invertible matrices, let's look, in some sense, a more natural problem. Let's look just at commuting pairs of n by n matrices. And let's at least start over an algebraically closed field. Okay, and so this is a variety, you know, nice algebraic variety. And it follows from the estimate before, from sort of Langevin or Deline's solution of the Weil conjectures, that the dimension of this variety is n squared plus n. And moreover, that's there's only one component of that dimension. All other components would have smaller dimension. But in fact, you don't need this counting to get this out. There's an old result, I think it's from 1955 in the transactions of the AMS, a result of Motzkin and Taussky, that the variety of commuting pairs of n by n matrices is an irreducible variety of dimension n squared plus n. And actually the proof of this is quite easy. And it's roughly the proof that they didn't put it in this language, but the point is every n by n matrix commutes with a regular matrix. That is a matrix whose characteristic polynomial is the same as the minimal polynomial. And from that, you can show that there's an open subvariety consisting of all, in the commuting variety, open dents of the form an arbitrary matrix and a polynomial in that matrix. And obviously those commute, and that turns out to be, that's pretty much all of them. So in characteristic 0, what you actually get that any pair of commuting matrices can be approximated by some matrix and a polynomial in that matrix. And this was extended to other simple E algebras in characteristic 0 by Richardson, and then by Paul Levy in good characteristic. And there you don't have that, the analog of that result is not true. So you have to work a bit harder to get this. So the point is, it's an irreducible variety of the dimension of the Lie algebra plus the rank of the Lie algebra. And a generic pair of commuting things is a regular element, one who's a regular semi-simple element, or whose centralizer is a torus, or the analog of the diagonals. And okay, so here's a curious corollary, which I certainly don't know of any other proof other than as a corollary of this, is that if you take two commuting matrices, then the algebra that they generate has dimension at most n. So this is if you think about it, this is a generalization of the Cayley-Hamilton theorem. And the way you prove it is that the point is that the dimension of the algebra being less than or equal to n is a closed condition, and it holds when A, say, has distinct eigenvalues, and that's an open condition. And so it holds on the closure, and so it's true. But we still don't know everything. You'd think this is a pretty simple variety. One should know about these things. But here's an open question. What are the smooth points of the variety? That is where the tangent space has the right dimension. And so there's a theorem of Neubauer and Saltman that said the smooth points are at least a subset of the pairs that actually generate an n-dimensional algebra. We know the dimensions at most n, but the ones that actually generate an n-dimensional algebra. And they would be, the conjecture is that, and in fact, they all are smooth. And the problem is you have the obvious ideal that defines this variety. We do not know if that's a prime ideal or not. If that's a prime ideal, then these are just by the Jacobian conjecture, not conjecture, by the Jacobian criterion, these would be all these points would be smooth. So we still don't know that. Okay, let's look at a variant of this. Let's take the commuting R tuples for more than 2. So Gerstenhaber noted that for 4 tuples, at least if n is bigger than 4, it's not irreducible. And he noted that there are 4 generated commutative subalgebras of dimension 5. And by the same argument that I gave basically before, if it were irreducible, any 4 generated commutative subalgebra would have dimension at most n. And so this fails. And then he asked what happened for r equals 3. So I proved that for n bigger than or equal to 32, this is not irreducible. And if you tweak the argument a little bit, once I wrote this down, some people fiddled around a bit and showed the same argument works for 28 or bigger. It's also known to be irreducible for n at most 11, and it's open for 11 to 28. Okay, and the argument I gave was kind of a really idiotic, simple-minded argument. So the point is, there is an irreducible subvariety component of this variety of dimension n squared plus 2n, namely the ones of the form a, f of a, g of a. And take the closure of that. That's easy to see. It's an irreducible component. It's the closure of some open subvariety, so it's a component. But what I computed was that for n big enough, that variety of commuting triples has dimension bigger than that. So there must be some other component. I have no idea what it is. I have no idea what its dimension is, and nobody does. So let me just point out. Let me just skip this. I think this was actually mentioned in one of the talks. So what's the largest commutative subalgebra? But anyway, let me just point out. It's sort of the upper quarter. Here's some open questions on these commuting varieties for r bigger than 2. What's the dimension? We don't know the dimension. I think it's not up to 7. I think maybe it's known, at least n equals 7, at least for smaller. And that's actually quite recent. Okay, so we don't know what the dimension is. How many irreducible components does this commuting variety have? Nobody has a clue. Again, except for small n. And here, this other thing is still open. Even if we know it's reducible, we do not know this. Is every 3 generated commutative subalgebra of n by n matrices, does it have dimension at most n? That's still an open question. We do not know the answer to it. So it's amazing how little we know. Okay. Here's a variant on this question. What if instead of taking commuting matrices, we take things that almost commute? And what do we mean by almost commute? We mean that the additive commutator has rank at most 1. That's pretty much as close to commuting as you can get. So Tom Laffey in characteristic 0 gave a proof, and then I gave a much simpler proof in all characteristics. He used trace identities. And it was fairly complicated. But if the commutator has rank, the additive commutator has rank at most 1, then they can be simultaneously triangularized. So over an algebraically closed field, you're in the Borel subalgebra. Here's a sketch. I'll leave it up for a minute. I'm not going to actually go for it. But this is the proof. It's either so okay. It's amazingly simple. So proof. So anyway, if you want to try to write it down, okay. And let's reinterpret this in terms of groups. So this turns out to has answered a question of Nick Katz about 10 years before he asked the question. If you take 2 invertible elements, 2 elements in GLN, and the multiplicative commutators are transvection, then the group generated by X and Y is solvable. And in fact, again, if it's algebraically closed, or as long as the eigenvalues are in the field, it's actually contained in a Borel subgroup. So it's triangularizable. And the point is, it's quite easy to convert this to the other problem. Just write down what the additive commutator of those things is. And I won't say much more about this, but this comes up, for example, if one wants to look at covers of elliptic curves with one ramified point for these kinds of groups that contain transvections, where the ramification, the inertia group of a point over the ramified point is generated by a transvection. And now one can also look at this variety of pairs A and B where the rank is less than or equal to 1. And I showed that the number of components is at least n-1 and actually wrote down n-1 distinct components. And Michael Neubauer proved that those were all the components, and they all have the same dimension. So this is an equidimensional variety. All the components have the same dimension, n squared plus 2n-1. And Hulek I think it was Hulek, proved that if you take rank bigger than 1, then the variety goes back to being irreducible, and you can write down what the dimension is very easily. So it's only when rank 1 is sort of the anomaly here. Okay, so what if we consider commuting pairs of p elements for some prime p? I'll say a little bit more about this, but if we go back to the case of GLN, or for Lie algebra, more recently, although it's not really that recent, by now I think it was maybe 20 years ago, Permet looked at this. So if you look at what would the analog of p elements be? Well, you take nilpotent elements in the Lie algebra, or if you're in an algebraic group, unipotent elements. And Barnowski showed for GLN C that this is an irreducible variety. And Permet proved it in any characteristic. Actually, Barnowski gave a geometric proof of it, because what he did is translate this problem into something about certain Hilbert schemes, and then use properties of Hilbert schemes to prove this. Permet used Lie algebras to prove that it's irreducible in n by n matrices, and use that to get a corollary about Hilbert schemes, which was not known in positive characteristics. So that was sort of nice that he did that. And in other, at least in good characteristic for the other Lie algebras, it turns out that the number of components is actually the number of distinguished nilpotent constancy classes or unipotent constancy classes. And so it's usually not irreducible. Type A, there's only one distinguished class. So, and the dimension is n squared. Okay. We're for GL, for MN. Okay. So what about for a finite group? And we pick a prime now, and we want to ask what's the probability that two random p elements commute? So that's sort of the analog of this nilpotent result, or unipotent result. And so if G is a p group, you can easily show that the commuting if either the group's abelian, or the probability is at most p squared plus p minus 1 over p cubed, and that's exactly happens when the center has index p squared. And it's exactly the same proof as for when the center has index 4. Okay, so anyway, so Gabriel Navarro and Alex Morato had worked on this, and they proved this for p-solvable groups and asked if this was true in general. And it is. So this is work that with Tim Burness and myself and Alex and Gabriel. So if G is a finite group, and then E, what is it? So what's the analog of being abelian? Well, you don't, all you're asking about are p elements, so you might as well assume your group is generated by p elements. And then if it's generated by p elements and any two p elements commute, then it's abelian, of course. But in general, if you look at the group generated, if all p elements commute and look at the group they generate, it's going to be normal and it's going to be abelian. So it's saying, oh, p of G is abelian and is the full Stilo subgroup. Or if that's not true, then the probability that two random p elements of G commute is at most p squared plus p minus 1 over p cubed. So it doesn't really matter that you take whether you take all elements or p elements in some sense. Okay. And in fact, what we really prove is something like this. There may be a couple of exceptions. I may be cheating a little bit, but in general, this is. Actually, I think this is actually true without any exceptions. If you take a p element that's not in the center of OP of G, then the probability that it commutes with a random p element is actually at most 1 over p. So the reason you don't get 1 over p in the end is because there are elements in the center of OP of G, namely the identity, at least, and that sort of skews it a bit. And in fact, you can assume in this, it's easy to prove that you can assume that OP of G is 1. So it's really the identity that sort of gets you to go down. But most of the time, it's not going to get you to go down that much. And in fact, you can classify the examples where you get equality. In the basic example, I mean, there are a few other examples, and you can tweak them a little bit. But the basic example is PSL2P. This has exactly p squared elements of order p, of course, and the number of commuting pairs is, well, either they live in a CLOP or one of them is the identity. And so that's how many commuting pairs there are. You can extend this to pi elements, where pi is some set of primes and p is the smallest prime. So that's what I meant in some sense. Knowing commuting of p elements tells you something about the commuting probability in the whole group. Okay, so how did we prove this? Well, so when Gabrielle asked me about this, I realized what's the probability that two random. So let's take two p elements x and y, and let's assume. Well, yeah, okay. What's the probability that a random conjugate commutes with a random conjugate of y? And you can relate this to certain fixed point actions. So let me define the fixed point ratio. So you have a group acting on a set of size n, and then the fixed point ratio for a permutation is just the number of fixed points divided by the size of the set. And this goes back a long way. This was studied by, it's related to the number of points moved by the element, obviously. It's related to it, but it's not exactly the same. And this goes back to Jordan and Manning in the 1800s, proved some really nice results. And it's come up in studying all sorts of things, Riemann surfaces, cutting covers of Riemann surfaces. It came up in Kleidman's proof of the Kegel-Wieland conjecture and subnormal subgroups and CELO subgroups. Comes up in probabilistic generation conditions. It came up in a very recent paper of Bhargava, where he gave a proof of van der Waerden's conjecture about the distribution of Galois groups of integer polynomials. Random, where random means you look inside some box, for example, and compute it in terms of the discriminant and the what the Galois group of the Galois closure of that polynomial is. And I'll just mention a couple of results. Babai really had a beautiful paper where, without using the classification, he proved, and I think Martin mentioned this in his talk about Jan on last Friday at Jan's conference, that if your group isn't AN or SN and you have a primitive group, then the number of points moved is at least roughly square root of n. And that's my second typo that I noticed anyway. And the examples there are roughly AN or SN acting on two sets, or basically like SN cross SN acting on N cross N, acting on N squared points. Or throw on a 2 on top if you want to make it primitive. Okay. Liebeck and Saxel proved that if you had simple group of Lie type, then almost always you get at most 4/3Q, where Q is the defining field, and they classified the counterexamples to that. And they in particular classified all the examples where you fixed at least you fixed to at least realized is that we needed to prove a better result. And what we proved was that if you have prime order P, then most of the time this fixed point ratio for primitive action is the most 1/p+1, or there are some specific actions that you know, like for example, symmetric groups acting on K sets or some things like that, and a few other things, transvections acting on one spaces and things like that. And in particular, this also improves the result I had with Chi to all things where something fixes more than 1/3 of the points instead of a half or 2/3. So what we do is apply this to something acting on the cosets of the centralizer. And of course, well, the centralizer may not be maximal, but it's certainly contained in some maximal subgroup, usually. I mean, unless the centralizer is normal, but you can sort of reduce to simple groups. We have, you know, I mean, we're talking about most things that are close to simple. And so the fixed point ratio of Y acting on G mod the centralizer of X, if Y is a P element, is at most 1/p+1. In fact, it didn't really matter that X was a P element most of the time. And so you get the probability that two elements from random constant class, random elements from fixed constant classes commute is at most 1/p+1, unless it's known. And from that and some work, you can get this result with Alex and Gabrielle and Tim. So we proved this commuting result. Let's see. And another, let me just mention one more consequence, and then I think I'll knock off. So if you look at, instead of the fixed point ratio, what people often look at is what was called the index of a permutation, which is n minus the number of orbits of G. This is also the minimal number of transpositions you need to write this element as a product of transpositions. And this comes up in coverings of smooth projective curves. It comes up in estimates in number theory, and it came up in what Mongeal did as well. This is really what he used, is was from fixed point estimates or points moved, you get estimates on the index. But here's a consequence of what Tim and I did, is that if you have a primitive group of even order, and you want to find some element of minimal index, which is exactly what Mongeal needed, then it always occurs for an involution. So you only have to look at involutions to see what this minimum is. Moreover, the only elements that can achieve this minimum are either involutions or, in a few very specific cases that you can say, some element of order 3. So for example, if you take the alternating group in its standard representation, the index of a product of two disjoint transpositions has index 2, but a 3-cycle also has index 2. And of course, those are the only elements that have index 2. So there are a few cases where you get equality, but most of the time it's just from some involution. So I think this is a good place for me to stop. And again, please, I want to thank everybody for coming and everybody for organizing this and everybody for the kind words they've said. The talks so far, up to this one at least, have all been extremely good. And thank you.
Does anybody have any questions for Bob? Anna.
Hi, Bob. It's Anel. It's great to see you.
Yeah.
and congratulations. I have a question. You had a result about multiplicative. The assumption was that the multiplicative commutator in for invertible elements of n by n matrices. Can the rank 1 assumption on this commutator be replaced by the commutator having a large centralizer with suitable interpretation of large?
No. As I said, for rank, anything that's ranked bigger than 1, even if it's tiny, it fails. So you can find things that I think that generate. You can find 2 elements. I'm not sure if this is true, but I think it should be true, at least for Q big enough, that you can find 2 elements whose commutator is that and actually generate. So it's transvections are very special. It even fails. So it works for symplectic group as well, obviously, because they're transvections, but it fails in general for long root elements, for example, and the other groups. It works in SP4 for short root elements by just applying the graph automorphism, but even for higher symplectic groups, short root elements fail. So it's amazingly special to transvections. And the proof is trivial, which is amazing, but it took forever. Nobody really thought about it for a long time, but it's not clear what's so special, why that happens, but no, so there seems to be no generalization of this.
Are there other questions?
I should say there is some analog for 3 cycles and alternating groups. And so there are some cases where you can prove a similar result for 3 cycles. For example, you cannot find 2 elements in AN whose commutator is a 3 cycle that generate AN, at least with suitable hypotheses. And Eamon O'Brien did quite a lot on that, actually. There was a problem on math.overflow asking about this. Coming from coverings of elliptic curves was the motivation.
Anything else? Okay, so let's thank Bob again, and then thanks, Bob. That was really nice.
Okay.
We now have a wine reception, so we've all got to do it again.
So please enjoy some for me.
We will. We'll look after it all. Good.